Okay, we are live on YouTube.
Okay,
If you have just joined the live stream, we will start soon. Just giving everybody the times to join. Thank you for joining us. We are waiting a couple more minutes to give everybody the time to join the live stream. So we will be starting in a few minutes. All right, welcome back to our series of live events at OrbitCamp. We hope you're enjoying your learning through the videos, exercise, and all the materials in the modules. Today, we are hosting Dr. Semak Ezar, who is the co-founder and CEO of Cayenne Space. He also holds a PhD in aerospace engineering from University of Colorado Boulder, with a focus on precise orbit determination. And that's what Dr. Ezar will talk about today. Dr. Ezar has also had the opportunity of supporting several NASA missions, including the Radio Science Working Group team, which was a team member for the OSIRIS-REx asteroid sample return mission. But without further ado, let me thank you once again, Dr. Ezar, for being with us today, and I will leave the stage to him.
Yeah, thank you so much for that introduction and for giving me the opportunity. Appreciate it. Hello, everyone. Yeah, today I'm going to talk about the challenges. So I titled my talk, "The Challenges of Building Robust Orbit Determination Software for Real-World Applications." You know, I'll just to set this stage up front is that I have done my best to minimize the amount of equations. So actually there will be maybe one or two equations at most, very simple. My goal here is to bring you some of the experiences I have had throughout working with supporting different missions and building orbit determination software for different missions with different requirements. So obviously, a lot of us in the astrodynamics community, we study the concept of estimation, orbit determination, and there's a lot of good work that is being done on the theoretical level, always taking that theory and implementing in a real world scenario, you almost always come across some issues that is not discussed in the theory, and you have to come up with, kind of a clever engineering type solutions to, basically deliver OD software to the real world scenarios. So the talk here in that sense is more of an engineering talk and operational talk. So with that, the agenda here is I'll just discuss a little bit about the main elements of an orbit determination software or a system. And obviously I'm going to abbreviate that orbit determination with OD from now on. And then we'll have a quick review of the OD filters just to level set everyone, right? So that in terms of what are the most commonly used OD filters, obviously orbit determination is a branch of in general the theory of estimation, and theory of estimation has been around for many years, and it has applications in many different industries and many different subjects, from robotics to face recognition to pattern recognition, different areas, or even in medical science. But obviously we take those concepts and apply it to the concept of determining the orbit of a satellite via measurements that we collect from Earth. And so as a result, I have a long section that focusing on the consideration that needs to be made on the measure models. These are the models that basically are used to really replicate what we are observing from a system, right? So there are a lot of consideration that goes to that. And then at the end, I'll close by reviewing some of the challenges that autonomous systems face. Specifically, when we talk about here, what I refer to autonomous systems, meaning autonomous spacecraft that is basically self-navigating in space, and finally the challenges of cislunar and interplanetary OD. With that, let's get started. So in terms of the components of an orbit determination software, so they're really at the very core of every, obviously, software and every system is written differently, but at the core of it, there are really three main components for an orbit determination software. One is the dynamical model, or dynamics model, it is referred to, which is basically, it is the set of libraries or software that is simulating the time evolution of the dynamical system. So basically, if we denote the state of the system as x at a time t, then essentially the dynamical model simulates the time evolution, or essentially the time derivative of that state as a function of time. And basically, the more accurate or higher fidelity this dynamical model is, the orbit determination filter has an easier job of estimating the state of that system. So in the application of an orbit determination, the dynamical model is basically our propagator, right? So how basically simulating a trajectory of an object at the presence of modeled force models as a function of time with a certain initial condition. The second main component is measure model. So this is very important, and basically that is a component that essentially simulates the quantities of the dynamical model that we measure, we observe, right, with any different types of sensors, and also it computes the discrepancies that we see between the computed values and the observed values, and that's really the key piece of information for an orbit determination filter to figure out, okay, the discrepancy based on the prior knowledge and what's the best estimate solution. Very similar to dynamical model, the more accurate the measurement model is, even more so, the measure model usually has a much larger weight on the orbit determination filter. In a real scenario, we need to make sure that our measurement model is as accurate representation of the real world as possible. So some of the notations here, I don't expect you guys remember it, but just so that we are aligned on the notations. So the capital Y, it's a vector of the observed observations. For instance, very simple. I have a satellite and I have a telescope tracking a satellite. We will get to the optical observations, but the azimuth and elevation measurements that I record in my telescope as a result of tracking that satellite, that is basically that Y, capital Y. The G of X, this is the computed measurement, right? So, and you can see that's a function of the state of the system, the dynamical system. So basically, this is where the measure model says that, okay, if I have this state of the dynamical system that I am tracking, so the state of the satellites that we think it is, then my computed measurement is such and such. And then the delta Y is basically the discrepancy between the two. And finally, obviously, the core of an orbit determination system, and that is the OD filter. Which is basically the biggest job of the main job of the orbit determination filter is to combine the knowledge that it has received from the prior knowledge from the dynamical system, as well as from the observed discrepancies from the measure model, and mix them together and basically figure out the best estimate scenario of the state of that system. And so X hat here identifies the best estimate scenario, and then P is usually specifies is a notation that people use to specify the uncertainty of the covariance matrix. So this is the uncertainty around the estimated state. So, and the kind of the interrelationship between these three different components are such that basically the measure model provides the discrepancies of the observed minus computed measurements to the OD filter. The OD filter, based on the prior information of the dynamical system, it performs the best estimate solution, provides that to the dynamical model, and the dynamical model provides the time update, so to speak, of the state, meaning that, okay, if I am given this initial condition, what is my prediction? And then obviously the best estimate solution also is provided to measure model to come up with the next step computed measurement. Okay, so a quick review of the orbit determination filters. So in general, if I want to classify orbit determination filters in two categories, we have what's called usually the epoch filters and sequential filters. And the most famous the epoch filter is obviously batch least squares filter. So that is basically the way the batch least squares filter works is that, again, we are specifically talking in the context of orbit determination and the motion of a space objects, right? So because batch least squares filter is used in other applications as well. So here I'm strictly talking about trajectories. So given an initial condition that is denoted here as x naught hat and the p naught, which is our initial knowledge of the state or the uncertainty of the state of the dynamical system, we can basically use our dynamical system evolution to come up with this trajectory into the future, right? And then what batch least squares filter does is along this trajectory, as we collect measurements and we record the discrepancies of those measurements, these could be hundreds of measurements in cases, or actually very few measurements in the sparse cases. But the key is that the filter collects all those information at once and performs a very large matrix manipulation of least squares solution of all these measurements collected that reflect the best estimate at the initial epoch. And that's why it is also referred to as the epoch filter, or meaning at the initial time. And then once I have the best estimate solution of my state, then I can use that to propagate it forward. So the pros of this method is it's usually more robust than sequential filters, because as you can see, it's kind of averaging, right? It is, since we are not very sensitive to a single measurements, after collecting all the measurements, and the answer that we get out of it is usually more robust to outliers than sequential filters. It has a fairly simple algorithm. That the core of the filter is literally a line of least squares, solution, matrix inversion. The cons are, obviously it is not real time, right? So you have to wait by definition to collect all these measurements and compute them before you are able to get the solution at a time that is passed already. So that is one drawback. And another might be a drawback for real-time scenarios, and that is it requires iteration, meaning that I will not go too much into the detail here, but hopefully in your program, you guys have covered, the linearization of a nonlinear system. So for instance, orbits by, inherently are nonlinear systems, the motion of an object in space. And batch filters, or in general Kalman filters, are linear filters most often than not. As a result, there is certain assumptions, linearization assumption, that goes into the formulation of the least square solution, for instance. So therefore, you have to iterate it over and over a couple of times in order to really get to the real solution. On the other hand, is the sequential filters. So obviously the sequential filters, as from the name of it is obvious, it is sequential, right? So, and basically, as opposed to the batch least squares filter, you have some initial estimate or initial knowledge. You can propagate it forward, collect the measurements, have the filter based on that one measurement or one set of measurements, perform another best estimate solution, and take that and propagate it forward again and again and again. So you can quickly see the fundamental difference here is that once you have gone to the next steps, you are accumulating the information, but in a case of, for instance, what's called the extended Kalman filter, since that relationship is broken, so to speak, meaning that now you have a completely new set of estimation of the dynamical system, you can't really go back. So that's obviously one of the drawbacks, but obviously the best pro is that it's a real time or close to a real time scenario. So for instance, onboard navigation filters or Kalman filters that are used to, for instance, collect the GPS observation of a satellite and generate solutions, those are always, in general, sequential filters. In general, this is a keyword in general, because there are certain sequential filters that you can iterate, such as conventional Kalman filter. But in general, the sequential filter does not need iteration. So basically, once you have at the epoch of the measurements, once you have the best estimate, you can move forward. The cons are it is sensitive to the solution, but I should have also said measurement outliers. So basically, if you have an outlying measurement, or you have a a sensor that is malfunctioning, then your filter solution can be skewed quite a bit. And there are ways to overcome that. I will go through that in a minute. And then finally, it's usually more complex algorithm than the batch least squares filter. Okay, so there are issues that obviously, like I said, as I mentioned, that there are certain assumptions that goes into formulating basically orbit determination filters, and as a result of those assumptions, we end up having certain issues. So basically, one of the main issues that a lot of the filters face, and that is the fundamental assumption of a batch least squares filter or a common filter is that the PDF, or probability distribution function of your object, is Gaussian, or following a Gaussian distribution. And obviously, we know that if you take a Gaussian system and propagate it or move it through a nonlinear system, which is an orbit propagation, then it will not, it will not remain Gaussian. Obviously, there are different levels of sensitivity to this non-Gaussianity in different filters, but it is an issue if you have to propagate your object for a very long time to get to the next measurement epoch. So as a result of, basically trying to resolve or get around this issue of non-Gaussian PDFs, people have developed other alternative filters. There are many others. This is by no means, encompassing a list, but these are the two more famous ones. The uncentered common filter, or UKF, that is essentially a mini Monte Carlo type, orbit determination filter that is able to propagate your uncertainty and state in a fully nonlinear fashion to the next epoch. And also particle Gaussian mixture models or filters, in general, filters that are based on Gaussian mixture models. So that is that, you can divide the uncertainty cloud of a state of an object into many small Gaussian elements or Gaussian distribution and propagate those independently and reformulate your PDF. The PGM is usually used in the context of research. In general, in the operations, I have personally seen that a lot of people either use UKF or even extended common filter or the regular common filter. And this is kind of this image from the paper that introduced for the first time the uncentered common filter. Really kind of shows in general the benefits of something like a UKF over a common filter or extended common filter, which is the linearized version. As you can see that a cloud of objects, if you propagate them forward using Monte Carlo, going through a nonlinear orbit propagation, it will lose its Gaussian shape. And you see that the ellipse doesn't even capture, nearly capture what that distribution is, versus the uncentered transform or uncentered common filter using this sigma points is kind of sampling from different parts of this particle cloud. There are other issues of orbit determination filters. One is another issue other than the non-Gaussianity or having to contend with non-Gaussian dynamics. The other one is numerical stability. At the end of the day, when we write the equations of an orbit determination filter, we can write it, but at the end of the day, when we have to implement it, we have to implement it in a computer software. And obviously computer arithmetic manipulation, there is limited amount of memory or the limited amount of precision the computer can go to, right? So, and as a result, we can have, if we have very large matrix, such as covariance matrix or information matrix that we have to invert, right? So the inversion of the large covariance matrices can result in numerical issues and instability, and suddenly your filter will fail because it is not able to, it's almost dividing by 0, and we will have singularities. So there are other filters that are introduced to contend with this issue. One is information filter, which is obviously, I'm not sure if people are probably familiar with this book, The Statistical Orbit Determination. It is basically, it's known as the Bible of the statistical orbit determination. So it's it's a very foundational book that whoever is interested in this domain, I would highly recommend getting one and reading it. So an information filter is described there as well as other places. So the difference of it between information filter and say a batch filter is that information filter works with the information matrix rather than the covariance matrix. So the information matrix is the inverse of the covariance matrix. So as a result, you don't have to invert matrix as you are doing your calculations. Another good benefit of an information filter is that if you absolutely have no idea a priori about the uncertainty, with the regular common filter or batch filter, you have to put a very large value in your covariance matrix, right? So for instance, you say that I really don't know where this object is in space, plus and minus 100 kilometers, right? So you have to put that 100 kilometers in your covariance matrix. Versus if you have zero information about your state a priori before you start the filter, when working with information filter, you can just start with 0. You have no information. So that makes it easier to use. And the numerical instability of the covariance matrix, either if it is a very large, but also if the condition number of a matrix is very large. And the condition number is obviously the ratio of the largest eigenvalue over the smallest one. So there are scenarios that in a given state of a orbit determination, we are estimating, for instance, the position of a satellite, which is a very large quantity, right, in kilometers, on the order of a few thousand kilometers. And then we also have to estimate, for instance, the clock drift, which is a very, very small, depending on your clock quality, it can be a very small value. And when we put both of those quantities inside a state vector and also inside a covariance matrix, then suddenly we end up with a covariance matrix that is not well conditioned and has a very large condition number. And as a result, to contend with that, people have developed square root version of the filters. And when you take the square root of a matrix, you essentially you cut the condition number by half, and as a result, you try to avoid the numerical instability that will result as a result of inverting that covariance matrix with very large condition number. And famous square root filters are the square root common filter or square root extended common filter. I put in my slides, I put basically the papers or the resources for these filters. I encourage everyone to go look at them. The SRIF or square root information filter is another good one that is basically the square root version of the information filter that is used heavily, especially in the interplanetary community. And it's a very robust filter. And then square root UKF. And that is also written by the same people that wrote the original UKF filter. They developed a year later, they developed the square root version of it, which is basically brings all the benefits of a UKF filter, and it is more numerically stable. Okay, now that we have covered some background and review of the orbit determination filters and their issues, I'd like to spend the next few slides in terms of looking at frequently used measurement models in different systems. Again, the list that I'm going to go through by no means is comprehensive, but these are the ones that are mostly used when we deal with the tracking of a space object. So the first one is rather simple one, and that is state solution, or the position and velocity solution of an object. And you might ask how you would get that, and you would get that by basically having a GPS tracker on your spacecraft. So, and the majority of the spacecrafts these days, they have, almost all of them, they have GPS is almost a standard component on the spacecraft these days. So having a GPS receiver on board for the caveat is that for the LEO spacecraft, right? Because they have to be below the GPS belt to see all the more satellites that they can perform the position solution. But those are details. I won't get into too much of that. But essentially, the GPS receivers, they provide either point solutions or kinematic solutions. So that's why I put velocity in kind of a different color, because you might not always get velocity solution from a GPS receiver. And sometimes it is derived from the position solution or point position solutions as an average between 2 point position solutions. So, and that's becomes not very accurate. Then another very commonly used measure model is obviously ranging, right? And I will go through multiple kind of flavors of these rangings measure models. GPS pseudo range is how the GPS receivers are able to measure the distance of the receiver antenna from the basically the GPS satellite, the center phase of the GPS satellite, and that is how they are able to basically solve for its position by getting the pseudo range from a minimum 4 or more satellites to be able to solve for the position of the receiver as well as the time. So the reason it's called pseudo range because it includes a lot of the errors in it. So it includes the in addition to the geometric range, which is here I'm showing as R. So a geometric range is basically the actual distance of the satellite from the GPS satellite. You have errors in the clock because your GPS receiver has clock errors, and we will get into that in a little bit, as well as many other sources of errors. These can be ionospheric errors, tropospheric errors for the Earth's regular everyday GPS usage that we have, not much in space, but also other sources of errors such as multipath and even delays in the electronics. Then we have one-way ranging. This is when basically the signal is sent, the navigation signal is sent from the your user satellite down to the receiver in a basically that's why it's called one way, right? So, and there are a lot of caveats here because, and I will go into detail of it, so I'll hold off on that, but that is one form of measurement. Another form is two-way, and this is also the radar ranging can fall under this category, as well as a lot of the interplanetary navigation. They perform two-way ranging, and the reason it's called two-way is because the transmitter and the receiver is in the same spot, right? So you have the ground system or another sensor. It doesn't have to be on the ground, but let's say for sake of our argument here, it's just the ground system. You have basically sending this navigation signal up to the satellite. It basically reflects from the satellite or goes through a very minimal amount of interaction with the spacecraft antenna and comes back, turns around. So that the one half of the lifetime travel between the spacecraft and the station becomes the range. And then we also have three-way ranging, and this is again used a lot in interplanetary. So from one DSN antenna, we send a signal to a spacecraft, and the other antenna receives it. Or also in the radar ranging, we might have radars, and there are quite a bit that the radar receiver and the transmitter are separate components, right? So, and they are separated in position, so in location. So you have kind of a three-way ranging there. Other sources, other frequently used measurements are range rate and Doppler. So we talked about range, measuring the distance. What about the velocity? So the range or Doppler measurements are basically allows you to directly measure the velocity of an object in your line of sight. So in the previous measurements, we only measured the location of that spacecraft at a given time and not the velocity. The velocity is resolved as a result of orbit determination filter and the dynamics. But obviously, it's much better to actually observe it, right? So that's where range rate and Doppler measurements come into play. And this is a kind of a cartoon of how the range rate works. Basically, the projection of your velocity vector over the line of sight, and the Doppler is very similar. Basically, the receiver measures the phase shift of the navigation message as along the line of sight. So I have a quick. Let me see if I'm going to be able to pull this off. So I'll stop sharing real quick and then go over the deep space network that I wanted to show. I think it's a very interesting resource and very relevant for our talk here. So let me share this view again. And I just clicked on that link that was on my slide. So that takes me to Deep Space Network Now. So if anybody Googles Deep Space Network Now, they will see this. This is the real-time communication of the Deep Space Network with all the interplanetary spacecraft that is out there right now. So as you can see, and the reason I wanted to show this because it's very relevant, you can see Lucy, which is a spacecraft, is doing a one-way communication right now. So there's a signal coming from Lucy down to DSN 53 in Madrid. Or Voyager, this is Voyager 1, that is talking with one of the large dishes in Madrid right now. And that is doing one-way because, two-way will be a very long way to go. Others, as you can see there, these are two-way communication, and we don't see any three-way here. So, we have Goldstone, California, and we have basically Canberra. So, SOHO, SPP, DSS, these are the satellites that are, we have MRO, MAVEN, and TGO, I don't know what the mission that is. So yeah, this is a very interesting site that you can go and play around and look at what's happening real world in the interplanetary navigation. So let me go back and share my slide again. Okay. So yeah, this is the link that is embedded in my slides. And again, as I said, the Deep Space Network Now. Other measurements that are very frequently used are optical measurements. So these optical measurements, there is a very good paper by Bill Owen from JPL, and that is methods of optical navigation that was written in 2011. And it goes in very good detail in terms of what are the different types of optical measurements and how to use them and all the equations behind them. So here I'll just mention a few. And I pulled all three of them. So, one of the most used type of optical measurements is basically tracking the the light signature of your satellite in space, right? So your satellite is very far from you, and then, or your target is very far from you, so it's just a dot in space. And basically what you measure is right ascension declination or azimuth or elevation, and the rates that associated with them over time. So that's how we track, most of the time, that's how we track debris objects in the geostationary belt, as well as other satellites and the satellites, right? So, and as well as, a recent advancement allows us to do LEO optical tracking as well. Others are more for the interplanetary and small body discovery or exploration, what's called the limb scanning or center finding. And this is when obviously your target, which is in this case is the picture of the moon, is much closer to you. So in the basically in your field of view, the object looks very large. But so as a result, you can start resolving the limb of the object, right? And then you have certain shape model for that object. In the case of a moon, it's a sphere, and we know the to a certain accuracy, we know its radius, so we can model what the moon should look like in a certain distance. And then if you are able to, basically scan the limb of the object, then you can find the center of it. And then based on your limb and the center, you can basically figure out what's the apparent size of that object from you. And that's how you can get measurement both from in terms of bearing, so the direction or the unit vector that you have from the center of the moon or another planetary object, but also the size of it, so the range that you get from it. This is not a very precise measurement. You can have kilometers of error, but when we are talking in terms of cislunar, orbital regime and kind of autonomous system, that's not bad. And then finally, what's called landmark tracking. And this is essentially when we get very close to an object, usually that object, landmark tracking is used in the asteroid exploration. And basically, by using or identifying the features on the surface of the object, you are able to basically do terrain relative navigation. And that's how also, for instance, autonomous Mars landers land on the surface using the terrain relative navigation. So the landmarking is kind of similar concept, that you are very close to the object, you can see features, and based on that features, you are able to basically perform optical observation of those landmarks. What are the common sources of errors of the measurements? Coordinate system is one of them. I'll get into it in detail in the next slide. Finite light speed. Light travels very fast, and navigation signals travel the light speed, but it is very fast, but it's not infinite. So that creates a lag, and that we have to model that very accurately if we want to get good solution in real time or real world scenarios. And one of the biggest source of errors is clock errors of the source, and I'll get into it in a second. Others are not as detrimental, but these can be resolved with modeling inside the filter. One that is often used comes up is per pass bias, and that is remember I was talking about that three-way ranging. So the three-way ranging usually happens that when a DSN antenna is locked on a spacecraft, and as the Earth rotates, then the other DSN antenna comes to view, so they hand off, right? And then in that handoff, the other, so even though one antenna was well calibrated and we knew the bias of it pretty well because we are tracking it with it for a while, now we have a new antenna, and then based on the how it gets a lock on the signal, there's going to be an unknown bias, and then that bias can actually change every pass from one pass to the other from the ground station. So that creates challenge, but that can be modeled in the filter. Other concepts that are actually called consider parameters. So quote unquote, considering the sensor uncertainties. within the filter without needing to estimate them. So again, this in the statistical orbit determination book, there is a chapter about how to implement consider parameters. Excuse me, and how to basically work to consider parameters into your filter and be able to account for uncertainties of, for instance, location of your tracking antenna as a function of time, right? So your location of your tracking antenna can change, or the delay and the electronics can change because of the the temperature outside of the things that you cannot control. But you have some idea in terms of what is the extent of the error, and you can consider, quote unquote, consider them in your filter. And then obviously relativistic effects. This is most relevant for GPS, for instance. So when we perform the GPS navigation, we have to account for both general relativity effects and as well as the special relativity effect that comes from the high velocity. So speaking of the coordinate system, one of the probably the most challenging coordinate transformation is transforming the inertial coordinate, which is usually J2000 or EME 2000, that is used to basically simulate the trajectory of a space object in space. It's an inertial frame to an Earth fixed frame. And the Earth fixed frame that is used is ITRF, or International Terrestrial Reference Frame. And ITRF is tied to the surface of the Earth. So obviously, when we are talking, for instance, TSN or any ground-based system, those systems are tied to the surface of the Earth. So their location is defined in ITRF. However, the location of the spacecraft is defined in J2000 or ICRF or another inertial frame. So there's a lot of scribble here, a lot of information. I don't expect you to completely comprehend in just one slide what's going on here. But what I'm trying to basically depict here is the complexity of going from the inertial frame to ITRF. Because when we talk about ITRF, we have to obviously take into account the precession of the Earth's pole, the nutation of the Earth's pole, which is the kind of a wobble around the precession circle as a result of sun and moon gravity, as well as even more challenging the polar motion. So this little curve that I'm showing here, it looks like a scribble because it is, because the polar motions is basically how the crust of the Earth moves over time. And that is not very well understood and obviously not very well predicted. So as a result, we have IERS, it's an international consortium that basically keeps track of all these parameters. These are called usually the Earth orientation parameters, or EOPs, and they are published on the internet. So any navigation system that is working in a real world scenario has to collect all that information on a daily basis. So those data are published daily in terms of what is the polar motion or polar location of the crust of the Earth at a given day, right? And this is one of the only, maybe one more of the math equation here, but this is basically shows the conversion of a position and velocity vector from J2000 to ITRF. So you have the precession. Did the recording stop? Oh, sorry.
Pause for a second, but it's on now.
Okay, sounds good.
And we also have a couple of minutes left.
How many minutes? Sorry.
Couple of minutes.
Okay, sounds good. I'll try to wrap it up very quickly. Yeah, so I'll go to the next slide. Other sources of error that we need to consider is obviously one is finite light speed. And that comes up in two ways. One is when we are talking about, orbital velocity is very high, obviously, and when you have a very large distance, when you are tracking and especially when you are talking about the one-way ranging, the time where the navigation signal left your spacecraft and received and got to you is basically by that time your spacecraft has moved, right? So the location when the spacecraft sent that signal is different than the location of the spacecraft is when you receive the signal. So that is, obviously we have to do an iterative process to solve for this inside the measurement model. If this is overlooked, you will have large errors in your measure model. Another way the finite light speed comes up is what's called a velocity aberration or stellar aberration. And that is basically the apparent position in the optical measurement when you're looking at an object that is moving at speed is different than the actual position of that object. So that also, there are equations that can correct for that. And finally, and probably the most important, is clock errors. And I'll go through it very quickly. So clock errors are two ways. One is the clock rate or the frequency error. It's also called clock drift. And this will show up most importantly in a one-way kind of ranging. Because when you are doing one-way ranging, you are trusting the clock that is on board the spacecraft. And if the oscillator of the clock of the spacecraft is different than the oscillator that you are using on Earth, then the frequency difference, the rate at which those different clocks tick, is going to result over time in a very large discrepancy. The good news is that you can either fix it by estimating it in filter, which a lot of people do, or you can use things like deep space atomic clock, which is a JPL developed hardware, or chip scale atomic clock, which are small form factor of very precise clocks that they tick at a very constant rate. Other is clock bias. There's really no fix for this other than basically estimating for it. So even if you have a very good oscillator on board, say a deep space atomic clock or a chip scale atomic clock, there will be a bias. It's almost you can't avoid it. There will be a bias between the clock on Earth of the receiver and your spacecraft. So, but then it's very easy to solve for the constant bias, or even dynamic bias, which would be as a function of the drift. I think I'm in my last two slides, so I'll go quickly. So now that we kind of talked about different challenges of the measure models and the sources of errors, it's a good time to talk about autonomous systems and what are the challenges there. And here, again, these are some of the ones that I have come across myself. I'm sure there are a lot more. But designing the robust filter, like I said, sequential filters can be very sensitive to measurement outliers. So if you have a fully autonomous system that is collecting measurements and processing the measurements, then if you have a sensor malfunction, or if you have a outliers always happen, then your filter can be fooled and basically go completely off the rails and diverge. So there are methods that people have devised to contend with that problem. Sigma gating is one of them, meaning that we are the predicted measurement uncertainty, basically based on the knowledge that I have from the sensor and my knowledge of the state. This is the uncertainty I should expect when I'm propagating to future. If I get a measurement that is way outside of that uncertainty, like more than 3 sigma, then I can easily deny that or reject that. Others are using parallel filters at the same time. So this used quite a bit, meaning, for instance, the parallel supervisor filter, moving window batch filter along with your sequential filter. So the way it works is that you have a main sequential filter that is processing the measurements and getting you state, best estimate state. But then at the parallel to that, excuse me, parallel to that, you have a batch filter that is in a certain window of time, and that is moving forward with your sequential. But since it's a batch filter and it is anchoring on multiple measurements, then it is not as sensitive to measurement outliers. So that can be kind of a supervisor filter. Make sure that your sequential filter is not diverging far off from your batch filter. Obviously, modeling clock errors is a challenge, and it's very important for autonomous systems to be able to accurately model the clock bias as well as the drift. And using atomic clocks on board is one way to reduce or minimize the error in drift. But obviously, over time, the error in drift accumulates, and you need to keep track of it. And probably the biggest challenge that is an area of research for a fully autonomous system is lost in space scenario, meaning that if you have a fully autonomous spacecraft and it doesn't have ground contact and it goes into a safe mode and it wakes up, it doesn't know if it was sleeping for 1 second or 10 years, right? So it has to wake up and orient itself and look at the environment and figure out what time is it. And that is a very challenging problem to solve. Finally, quick points on the challenges of the cislunar interplanetary OT. So obviously the long distances here is a challenge. So being able to close loop or the closed signal between long distances from the ground-based tracking, the size, weight, and power matters, especially when you're talking about smaller spacecraft that relies on the ground. So it's a limited resource, right? So there are very few ground systems that are capable of tracking cislunar or interplanetary spacecraft, and those are few commercial providers, as well as just DSN and European Space Agency and JAXA, as far as I know. So and those are always on demand. So being able to perform autonomous capabilities is definitely a desire, but also that comes with its own challenges, as we talked about. And that's the next bullet. And then there are a lot of research that is being done on in this area actively in terms of cislunar environment as well as interplanetary. What are the other measurement sources that we can utilize or signals of opportunities that doesn't rely on ground? So we don't need the ground to track our spacecraft all the time. So these are we can actually use. Turns out we can use GPS signals well beyond geo and above. So we have had NASA has had demos of this, and we have used this in the past. Obviously, optical measurements. Stars are everywhere. Planets when you're and the moon when you are in the cislunar environment, then you can utilize those observations to navigate the spacecraft. And the most recent and more of a kind of a research topic, XNAV, or basically using pulsars and to kind of natural GPS sources to be able to navigate yourself in deep space. With that, I put this reference here. This is a really good reference. It's a NASA report that came out recently in 2018, written by Russell Carpenter and Chris D'Souza. They both are amazing in field of orbit determination and navigation. And the report is Navigation Filter Best Practices. It's a reference, more of a paper, more than a paper. So it's a very good reference for everyone that is working in this field. With that, thanks so much for your attention. Sorry, I ran a little bit over time, and I'm happy to answer any questions.
So the first question that I'll ask is from one of our listeners today. Rahman asks if there are any missions that shift from two-way communication to three-way communication when the satellite is eclipsed from Earth by its host planet. So is there a case where you go from two-way to three-way, or do you usually stick with like one type of communication?
So two-way and three-way is usually used by DSN, and that is just mainly tracking or only tracking interplanetary spacecraft. And the way that happens is that, as I said, if you are in the middle of a navigation campaign, let's say we are tracking Mars Reconnaissance Orbiter, and basically, let's say Madrid has a lock on it, but then it is, Earth is rotating over time, so after a while, Madrid is kind of going out of sight, and we have to hand it off to another station, maybe in Canberra. So, in a very short amount of time, three-way is not used for a long time, but it's a kind of a handoff between one station to the other.
Got it. When you're operating in the cislunar space, do you have any additional uncertainties or error sources that might not occur if you're just operating in low Earth orbit?
Yes, in many ways, there are very different environments. And in many ways, the orbital dynamics of the cislunar space is much well defined compared to Earth or LEO. And the reason is that in LEO, we have the Earth's atmosphere and the drag, which is a largest source of error. And obviously, predicting atmospheric density is extremely challenging. It's just like, predicting the weather on Earth now, let alone predicting the weather in space, right? So in many ways, dynamical models are a lot more accurate for the interplanetary or cislunar environments. Then they are much well understood compared to the LEO environment.
Awesome. We have another question from Raman. So his question is, can we solve the lost in space problem by analyzing the half-life? So I guess the example is your spacecraft's operating, then it shuts down. Can you look at like the half-life of an RTG, a radioisotope thermoelectric generator, to kind of determine where you are? Is that even a solution?
Yeah, that's not my expertise, so I won't comment on that. But yeah, I mean, one of the active researches that is being done is by looking at the location of the planets, right, and their moon. So if you have a very good capable telescope and you are able to detect where Mars is, where Jupiter is, where Mars's basically satellites are, where the moon is, where the Earth is, you can kind of figure out what year you are or what month you are.
That's pretty cool. And then lastly, what is the hardest piece to implement in OD software, in orbit determination software?
I think that writing the software itself is the hardest piece. To be honest, that's been my own experience, because again, at the end of the day, writing the math equations, even though coming up with the equations is difficult, but you can always write them and say, okay, inverse of this matrix, all that stuff. But when you're actually implementing it and you are coming up with all these numerical issues, one of the biggest challenges of embedded softwares or onboard solutions is limited capacity or limited memory or limited speed of a processor. So those are, to me, the engineering challenges is much harder to solve. There's not a textbook, kind of remedy for doing that.
Absolutely. So we are slightly over time, so I think we're going to end now. So thank you so much for that really interesting talk. And I think I learned a lot about orbit determination. So thank you so much for joining us today.
Absolutely. Thanks so much for having me. And sorry, I ran over time. Thank you.